Hello, thanks for joining me as we begin a new subtopic in our chemical energetics unit, exploring the idea of entropy. Where today, aptly enough, we'll begin with an introduction to entropy, where we'll understand entropy as a measure of the disorder of a system. Now, entropy, it's a really fascinating topic. It's somewhat conceptual, somewhat abstract. It can be a bit tricky to wrap your head around it, but once you do wrap your head around it, which you very much will, it's got these really interesting implications for, the universe we live in, very macroscopically, but more importantly to us, the chemical reactions that we investigate in chemistry. It's a concept that we can use to explain some things that perhaps we've taken for granted at this point. Why do some reactions occur spontaneously whereas others don't? Why are some reactions reversible whereas others are not? But to really understand it, which is what we're going to try to do today, we'll just spend this lesson really getting into the nitty-gritty about what entropy is to help us, extrapolate further to some bigger concepts in chemistry. We've got to begin by looking at the three laws of thermodynamics, which I've put in brackets simplified there. Simplified, so my little brain up here can understand it because we're getting a bit physicsy. So the first one refers to the conservation of energy. These conservation laws, we've seen a lot. Conservation of mass, conservation of matter, the idea that, chemical reactions have to be balanced because you cannot create matter, you cannot destroy matter. All matter that has existed in the universe will be the same matter that does exist in the universe. Same with energy here. Energy is conserved. It cannot be created and it cannot be destroyed. The energy in an isolated system is conserved. And we've been using this law without, putting a name on it so much with all the stuff we've been looking at in our energetics so far. We can use this first law to apply to things like Hess's law to build these entropy cycles. These are based on the conservation of energy. We can also use it to determine the efficiency of a system, which feeds into the next two laws. The second law being the quote-unquote disorder in the universe is always increases, and as it does, energy is transformed into less usable forms. Thus, the efficiency of any system is always less than 100%. So you think about energy transfers. You've got many different forms of energy: electrical energy, chemical energy, kinetic energy, so on and so forth. And there can be conversion between these forms of energy. However, no energy transfer is 100% efficient. There's always some amount of energy. It might be a very small, perhaps one could say a very insignificant amount of energy that is converted into essentially a useless energy, a less usable form. No process can have 100% efficiency. And this is why something like a perpetual motion machine, if you go on, Google Images and you type in some perpetual motion machines, there's these great machines where if you look at them and you think about them, how they would operate, you go, well, that surely can generate an infinite amount of energy. But there is no 100% efficient process. So even these perpetual motion machines are always going to have a small amount of energy loss that is, transformed into a lost form of energy. Thus, they can't keep going perpetually. You got to obey the laws of thermodynamics, unfortunately. Now, I've used this word disorder. I'm intentionally not dropping entropy in these laws, which many definitions that you see will do, because I don't want us to just think about that so far. I want to just think about disorder. The third law, the disorder of a system approaches a constant as temperature approaches absolute zero, which is minus 273 degrees Celsius, aka what's known as 0 Kelvin. Kelvin being an absolute temperature scale, whereas, degrees Celsius or Fahrenheit, they're relative, they're arbitrary. Degrees Celsius is putting 0 as the freezing point of water and putting 100 as the boiling point of water. Why do that? Well, because water is something that's pretty tangible to us as conscious human beings, isn't it? Something we interact with and can refer to. Fahrenheit, don't know. I'm sure it's working somehow. But Kelvin is absolute. So Kelvin says that at zero is the minimum. Well, it's nothing. It's the bottom. You can't go below 0 because at this temperature, all molecular movement ceases. So, heat, molecules moving, kinetic energy. Essentially, we can think of heat as how much kinetic energy the molecules have, the particles have. At 0 Kelvin, they essentially have zero movement, zero vibration, there's zero energy. So at this temperature, all molecular movement ceases, so a perfect crystalline substance has no disorder. Disorder. I keep using this word disorder. Let's talk about disorder. And you can think of disorder in, your everyday vocabulary. You've got something that's ordered, nice and neat and organized, something that's disordered. The opposite of that. It's messy, it's chaotic, it's random. So we can think of disorder in those terms at this point. So this second law that talks about the disorder in the universe is always increasing, well, we can think of that as the energy is getting less usable. The disorder of a system approaches a constant where it has no disorder at absolute Kelvin. Well, it's perfectly ordered, it's perfectly organized. And what's occurring is the universe is always tending towards disorder, which is a great little snapshot of a sentence, I think. But let's think about what this means. This is telling us that disorder is an energetically stable form. So because the universe is tending towards it, the disorder, our second law, the disorder is always increasing. There has to be something driving, for lack of a better word, something driving that direction, that tending towards disorder. So what is disorder? Like I said, the opposite of order. Let's have a nice, neat hexagonal pattern. That's all. It's not a hexagon color. There we go. Geez Louise, can I draw a hexagon? Do it like that. This is nice and neat and ordered. We got a nice, organized, repeating pattern. Loving it. So let's say if that's ordered, what's disordered? Well, my hexagons are all over the shop, doing whatever they like. Order versus disorder. Think about a messy house versus a clean house. The universe tends towards disorder. Think about leaving your house and not doing housework for a while, which is what my house is looking a bit like at the moment. But your house gets messier over time. Your house doesn't sporadically get cleaner. I mean, that would be brilliant if it does, doesn't it? But it doesn't. It gets messier. So the messier house is easier to achieve over time because we're tending towards that disorder. It's a more energetically stable state when it is disordered. So we can think of entropy being a measure of this disorder. We can pop some calculations, we can pop some numbers, and it will tell us how ordered or how disordered the system is, how random or unrandom the system is. And this is what you're going to hear entropy, sort of the one sentence definition to what it is, entropy as a measure of disorder. We're really going to get down in the nuts and bolts of this and start to look at this in terms of things like statistics and probability, and the fact that disorder, well, you can think of it on a probabilistic scale. The fact that it's more probable to be disordered than ordered, and then we can extrapolate that as a concept to our chemical reactions that we'll see later on. So entropy is given the symbol S. Why is it given the symbol S? Well, what did I write here? Well, named by Rudolf Clausius, little name drop as we do, a German physicist, mathematician. He named it after the Greek word entropy, funny that, which means transformation. And you might go, well, entropy, that's sort of sounding a lot like enthalpy. Couldn't they have picked a different word? And from what I was reading, it was an intentional thing that he did, because entropy and enthalpy, as we'll see, are very, very interrelated. We've already been talking in terms of entropy and energetics, so it was intentional that he made the words so similar to one another, because Clausius found them to be so interlinked. Given the symbol S, it's kind of unclear as to why. A common theory seems to be that he did it in honor of a French physicist named, pardon me French, but Nicolas Sadi-Carnot. Although it seems like that's pretty disputed, so I wouldn't go regurgitating that. But if you're interested, that is one such theory, but we don't have to care about that. Entropy, S, is a symbol, is a measure of the dispersal of energy at a specific temperature. So we can put this in mathematic terms. So we have S, which is our symbol for entropy. Delta, we've seen deltas before. We've seen delta H's, delta T's. Delta means change. So we're looking at the change of entropy here, is the amount of energy per temperature. So Q is the energy, given the symbol joules. T is the temperature, energy per temperature, which we're dealing on our absolute scale, Kelvin, our SI units for temperature. So joules per Kelvin are the units that are given to entropy. So we can already see energy, entropy, enthalpy, energy, being somewhat synonymous. They're quite interlinked here, aren't they? The higher the randomness or the disorder of a system, the greater the entropy that system will have. So you can think of entropy as the dispersal of energy, either from the system to the surroundings or the vice versa. So I've got a little sort of analogy I'm going to bring throughout this lesson here, where I've got a lovely little puzzle, which hoping it doesn't fall down. Little 64-piece puzzle put together in a very, you guessed it, a very ordered, a very, organized structure, highly ordered. So we could say, if this hopefully doesn't fall off and I have to put it together again, we could say that this has a very low entropy in our puzzle here. You might guess where I'm going with that later on when we talk about increasing entropy. So you can think of entropy as the dispersal of energy from systems to the surroundings or vice versa. So when we're talking in chemistry, and what we'll be looking at, we're talking about the system as a chemical reaction. That's what's important to us. And our surroundings can be numerous things. We've talked about surroundings before. If we're doing it in a solvent, if we're doing it in a container, if you're just feeling the air particles around it, you can interact with the change in energy in these surroundings. You can feel the solvent increase in temperature, decrease in temperature. Same with the air, same with the container. You might have a thermometer in there that is also acting as the surroundings, so on and so forth. As the system becomes more disordered, it becomes energetically more stable. So this is our second law of thermodynamics, which I think is the main one we'll be looking at. But the disorder in the universe is always increasing because this disorder is energetically stable. So from here, we can start to use somewhat the words disorder and entropy interchangeably, synonymously. So if we think about the entropy is always increasing because increasing entropy as a measure of disorder, is a more energetically stable state. So let's talk about disorder a little bit more. I was talking on a macroscopic scale, the little puzzle, my messy house, so on and so forth. We're not worried about houses and puzzles in chemistry. We're worried about particles. We're worried about the small molecular atomic scale, aren't we? So let's think about these concepts on this much more tiny size scale. Consider us three states of matter. And I've gone and drawn a classic particle diagram representing the solid, representing the liquid, representing the gas. Which do you think, based on my diagrams here, would be the most disordered? And I'm sure what you would assume, what you would guess is, or what you would guess, not what you would guess, but gas is the most disordered system. We have a nice, neat structure where we have particles in a fixed lattice, in a fixed position, vibrating, compared to these ones over here, moving with high kinetic energy in random directions, colliding with each other, colliding with the container. Of course, the gas is a more disordered system. So we've got an increase in entropy between the solid going into the liquid, going into the gas. So let's stay with our gas here, and let's consider another instance of order and disorder. Consider the diffusion of a gas. So diffusion being the movement of particles randomly from an area of high concentration into an area of lower concentration. Which do you think would be the more disordered system? I've got two jars here with gas A and gas B. And then I've got a system over here, again with two jars, but gas A and gas B have now mixed together. Which one do you think is the more disordered? Well, of course, it's going to be the gas jar or the gas jars on the right-hand side. This one is going to be more disordered, the same way our gas was more disordered than a solid. When they're all mixed together, that's more disordered than when they're nice and separate there together. So the question becomes, why do the particles mix at all? Why don't they just stay like that? Why don't the particles completely swap gas jars? You wouldn't expect that to happen. You wouldn't expect all my green gas particles to just totally swap place with the purple gas particles. It becomes a bit of a intuitive thing that, of course, you're going to get a mixture of it. Why, oh why does that happen? So we've got the diffusion as the random movement and collision of molecules from an area of high to an area of low concentration. And it just comes back to these ideas of chance and probability. The fact that disorder tends to increase because it just becomes a more probable outcome. What would this be expected as a result after mixing? So if you consider this and then we let it mix and we end up with that, would you expect that to be an outcome? Well, I would assume you would say no, that wouldn't be a likely outcome. It could be an outcome, but it's not a likely outcome. There is a very low chance of this occurring. There's only one possible state that can occur for this arrangement of our gas particles to be the final outcome. But there are a number of possible states that occur when the molecules become mixed up. So disorder is a more likely outcome. All right, let me go back to my puzzle here. So, we can think of my puzzle. This is the nice ordered structure, but, and I hope I don't need to remake this for any uses later on, but I'll smash up my puzzle. All right, now we got order. Sorry, now we got disorder. We've got chaos. All my puzzle pieces, well, they're all over my desk now. So you think about doing a puzzle, right? There is only one possible outcome where you made the puzzle as it's meant to be. You've got to put all your pieces in one specific arrangement, relative to all the other particular. There's only one possible outcome. But you think about the disordered puzzle. That's disordered. That's one outcome of my puzzle pieces. I might just grab a little sample here. So let's say I've got a sample of puzzle pieces there. I jumble that up. I've got another disordered system. You might say as disordered as the last one, but that's a different arrangement of those pieces. They're still disordered, but they're disordered in a different arrangement. So let me shake it up again, and we end up with another disordered arrangement, different from the first two, but still, as disordered, you could argue. So that's where this idea of probability and entropy become linked together, because disordered outcomes are just much more likely to occur than ordered outcomes are. So what this means is that entropy is an emergent property. An emergent property you might sort of encounter in a field like biology, perhaps a little bit more. But an emergent property is something where the individual parts don't have that property, but when they all come together, they do. What do I mean by that? It's the idea that, the whole is greater than the sum of its parts. So the system has properties that the individual constituents of that system do not. So take something like consciousness, to talk back about biology. No individual cell in our body is a conscious cell. However, when all the cells, come together and they're interacting with one another in whatever way they do that, we end up with a property that our system has. Our system in this case being our human body, it has the property consciousness that no individual part in that system has itself. Entropy is the same thing. This little puzzle piece here, this puzzle piece doesn't have entropy. But all of a sudden, I put a few puzzle pieces together. These puzzle pieces as a system together now do have entropy. It's an emergent property. The whole is greater than the sum of its parts. So what is entropy doing? Entropy quantifies the number of microscopic configurations, what are called microstates, that are consistent with the macroscopic quantities that characterize the system. E dot G, the volume, pressure, temperature. What the heck does that mean? Let's keep exploring a little bit further this idea of entropy as a measure of uncertainty. Let's go back to our diffusion example. Let's take a bit more of a simpler system here. We had numerous gas particles over there. This time, let's take 3 gas particles in a jar. Now, these 3 gas particles are all identical to one another. We could say they're all a helium atom, they're all a neon atom if you'd like. I've represented them with different colors so we can keep track of where they're moving. But just bear in mind, this is important later and I'll reiterate it later, they're all identical gas particles. Consider where we've got 3 gas particles. We have a partition, stopping these particles moving between the 2 gas jars, but we then remove that partition so that particles from jar A on the left-hand side, we'll call that jar A, can now move into the right-hand jar B. What possible outcomes, of which there are 8, if you want to pause and maybe draw out these possible outcomes, how many different arrangements of gas particles between jar A and B can you possibly have? If you want to do that, give it a pause and we'll do it now. Let's have a look. You would have this. So let's think about this step by step. We remove the partition. One possible outcome, all 3 gas particles stay in jar A and we have none in jar B. We could have the blue gas particle move over to jar B. So we end up with 2 in jar A and 1 in jar B. We could not have the blue one move over, but instead the red one moves over and the blue one stays. This still gives us 2 in jar A and 1 in jar B. Or the third possible outcome with 1 moving over is the red and blue stay and the pink moves over, in which case we've still got 2 in jar A and 1 in jar B. Other possibilities is we have 1 gas particle stay in jar A and 2 of them move over. Now it could be that the red and blue move over. It could be that the blue and pink move over, or it could be that the red and pink move over, and that gives us 3 possible outcomes for 2 gas particles moving over. Or our third outcome is all 3 gas particles move over and we end up with none in jar A and we end up with 3 in jar B. Now, each of these outcomes is as likely as any other one of these outcomes. So let's say our 3 gas particles is as likely as having the red and the pink move over and the blue move over. Those 2 outcomes are as likely as each other. So you can pick any 2 outcomes and say they're as likely to occur as any others. What's important here though is that these 3 gas particles are identical. So some of these outcomes become equivalent to one another. Therefore, some of these outcomes do become more likely because there are multiple ways that you can have the same outcome. Each of these outcomes are as likely, as equally likely to occur as each other. The chance of any one of these outcomes occurring is a 1 in 8 chance. So the chance of that is 1 in 8. The chance of that is 1 in 8. However, this can be expressed as 2 to the power of 3. So we got 2 gas jars with 3 gas molecules gives us a total of 8 possible outcomes. But if we take each molecule as identical, some outcomes are equivalent. Thus, certain outcomes do become more likely, which is what I want us to explore together now. So let's consider a good old frequency graph for our outcomes. If I remember how to draw my straight line. Oh, that's not a straight line, it's a curved line. There we go. So let's have our frequency of outcome on the y-axis there, and then we'll have our possible outcomes on the x-axis there. So what are our possible outcomes? Well, we could end up with 3 in jar A and 0 in jar B. So if I say 3 in A, if we just focus on A. Next, possible outcomes is we could have 2 in A. So we could have 2 in A there. Then we could have 1 in A, and then we could have 0 in A. Our frequency, we could have, let's just go 1, 2, 3, 4, like that, because we're dealing with a pretty small sample size here. So what's the frequency of the outcome of 3 in jar A? Well, there is one possible outcome. So let's bring this up to 1 there. Sorry, I'm getting bogged down and getting my drawing perfect there. Now we could have 2 in jar A. What's the possible outcome? Well, there's 1, 2, there's 3 possible outcomes. Again, we're assuming all 3 of these molecules are identical to one another. So that would mean there's 3 possibilities of having 2 in jar A. Again, we got 3 possibilities, 1, 2, 3 possibilities of having 1 in jar A. And then we've got 0 in jar A. Same with our 3 in jar A. We've only got 1 possible outcome for that, like that. Now, just for my own peace of mind, I'm just going to move this a bit more central because I like it when it looks a bit more consistent. So, what are the ordered outcomes? Well, the ordered outcomes, like with my puzzle, is when the puzzle was made. Everything was in the right possible configuration. So our ordered outcomes here, they're going to be where we've got all in one jar or we've got none in one jar. So we could say that our ordered outcomes, we could say that all in jar A or none in jar A, these are more ordered outcomes. Ordered, I think that's how you spell ordered. And then if you think about the disordered outcomes, if I get a nice little green there, our disordered are where we have, gas particles in both jars. So these can be our disordered outcomes. So what is the probability of having a disordered outcome? Well, we've got 3 there, we've got a total of 6 out of 8 possible outcomes for a disordered. Whereas our ordered, we have 1 there and 1 there. We have 2 out of 8 possible outcomes. So, if we think about, again, entropy as a measure of disorder, well, we can see that the higher the entropy, the more disordered, the more likely the outcome becomes. We've got 6 out of 8 of being disordered, whereas we've only got 2 out of 8 as being ordered. So entropy becomes a likely outcome. Now, very much is the possibility that we still do have an ordered result. However, like I keep saying, that's less likely. I could drop my puzzles just on my desk here. There's a chance that if I drop them all together, they all fall perfectly in position with one another and end up to perfectly make that puzzle when they drop. That's possible. Is it likely? Most definitely not likely. It's very, very unlikely. We're seeing a very, very sort of similar idea here on a smaller scale. So which systems are ordered, which are disordered? We just did that. What is a more likely outcome? It's the disordered outcome is more likely to occur. So we're dealing with a very small scale here. We're dealing with 2 to the power of 3, which is 8 possible outcomes. Let's scale this up. Let's scale this up to my example I just used, my puzzle. Let's say we got 64 pieces. Now, this doesn't exactly translate, but let's say we had 64 gas molecules in our 2 jars. How's that for making it translate a bit more? Well, all of a sudden, we end up with 1.85 times 10 to the 19 possible outcomes. So by increasing from 3 gas particles to 64 gas particles, we've increased the amount of possible outcomes astronomically. In a chemical system, we're never going to have 3 gas molecules, are we? We're never going to have 64 gas molecules. We deal on the scale of moles. We deal with huge amounts of atoms. So let's scale this up to 1 mole of gas particles in my two jars? Well, we got one more. We have Avogadro's number. We have 6.0, this is still on the screen, 6.023 times 10 to the 23, which you can imagine the amount of possible outcomes is astronomically high. Astronomically high. Hope that's how you spell astronomically. You know, you deal with another jar in there. You deal with another mole in there. The amount of outcomes that are possible become unfathomable. Now, what's happening is, if you think about it at an ordered system, if you think about having all of the 1 mole of gas particles in one jar, well, you end up with a 1 out of 2 to the power of Avogadro's number, which is, boy oh boy, that's a big old, no, that's small. That's a very, very small number. That's 0.000, who knows how many zeros before you get to your digits. Tiny, astronomically small possibility that you would have a ordered outcome, which for all intents and purposes, you know, for all our practical purposes, is an impossibility. The odds are that small that it becomes just such a remote possibility of an ordered outcome being likely. All right, what have we got over here? So yeah, consider this, scaling this up to, you know, a more realistic scenario, not 3 gas molecules, but a mole of gas. You know, chuck another mole, 2 moles. These numbers are becoming massive. So the possibility of an ordered system with a mole of gas is just unfathomably low. So this is what we mean when we keep on saying, or I keep on saying, that, where did I say it? Disorder is a more likely outcome. Now, that's not to say that you can't make something more ordered, but in order to do that, you've generally got to put energy into the system. I've now got a whole bunch of puzzle pieces on my desk here, which I could sit down and I could put the energy in to make that puzzle again. Sure, why not? Sounds like a fun little afternoon I have ahead of me. What's not going to happen is the puzzle isn't spontaneously going to remake itself just through likelihood, through probability. You know, if I kept dropping those puzzle pieces, I would have to do that an astronomically large amount of times before it just happens to find itself in an ordered system again. So that's what we're talking about entropy as a measure of disorder. So consider scaling this up to more realistic scenarios. You know, more moles of gases, more jars. The amount of outcomes becomes bigger and bigger and bigger and bigger, where the likelihood of those ordered outcomes, the possibility of ordered systems, become more and more unfathomably unlikely. Thus, the entropy is always increasing. Think about this, if you like, on your bell curve, if you're into your maths and your statistics, which I'm sure you are. You've got, you know, more and more divisions you can put down here, more and more possible outcomes. Our ordered outcomes in the center there, these become far more likely, and our disordered outcomes in the center there become more and more likely, where our ordered become more and more unlikely. Entropy as a measure of disorder, where we have disorder increasing due to these probabilities we've been looking at. Fabulous. We can consider the lesson finished there, but I want to finish just with a bit of a thought experiment here, where we're getting a little bit out of my realms of expertise, but it's so fascinating when you think about implications of entropy, you know, the implications of entropy always increasing, disorder always increasing. What does this mean on the time scale of our universe? So let's just finish with a bit of a fun little thought experiment here. Consider our first 2 laws of thermodynamics. First law, conservation of energy. We cannot create energy, we cannot destroy energy. All energy that is will be all energy that will ever be. And we've also said the second law is that disorder we can now substitute that word with entropy. If you'd like, the entropy in the universe always increases, and as it does, energy is transformed into less usable forms. So there's a finite amount of energy. No energy transfer is 100% efficient. Some energy is always lost as unusable energy. So take that to its natural conclusion. What does that tell us? That tells us that the amount of usable energy is eventually going to run out. What does that mean for the fate of our universe? We can also think of entropy increasing with time. You'll often hear this referred to as time's arrow. So the disorder in the universe always increases. We're thinking increases across time. As it does, energy is transferred into less usable forms. So how do you decrease energy? How do you decrease entropy? As far as we know, entropy cannot be reversed. What would reversing entropy look like? If entropy increases with time, to decrease entropy, do you have to reverse time? Are we talking time travel now? I'm not saying it. So as far as we know, entropy cannot be reversed. And what will happen when entropy reaches maximum, when all energy is transformed into non-usable forms? And this comes into one of the theories, of which there are a number. One of the theories about the ultimate fate of the universe that we'll be living in. So before we discuss that, let's talk about the start of the universe, what we know as the Big Bang. The universe expanded from an initial state of high density and high temperature. Just after the universe started, the universe had a very low entropy. It was very, very ordered. So if we say that entropy is always increasing, does that mean at the very, very start of time, the very start of the universe, entropy must have been at a minimum? So the order was very, very high. It was very, very ordered, a very, very low entropy. So if energy is being transferred into less usable forms, what does this mean for the ultimate fate of the universe? So one theory, the same way the Big Bang is the theory of the birth of the universe, one theory for the death of the universe is what's called the Big Freeze, aka also known as the heat death of the universe. One potential theory on the fate of the universe. The universe is heading towards a state of no thermodynamic free, useful energy. So each energy transfer is losing some energy into an unusable form. Eventually, the energy will be completely lost to unusable energy, and there is no useful energy left in the universe. This means no work at all will be possible. What would that look like? Well, you can use your imagination there. I'm assuming it's going to be a pretty bleak, cold, dark, uninteresting place. Not to stress though. We're dealing on the times of, I'm sure billions of years, so it's not going to affect us. But just something interesting to consider, isn't it? If you take this concept of entropy to the nth degree. And in fact, there's a really interesting little short story I'd recommend. What if entropy could be reversed? There's a short story called The Last Question by a famous science fiction writer called Isaac Asimov. Just a short one. You can find it online if you're looking for something to do, something to get your creativity, get your thoughts going. And in fact, there's also some really, really interesting animations that people have made, which are worth checking out. I'd go for the book over the animations, but they're free online on YouTube as well. So if you do find it an interesting topic, really interesting little short story there about what if entropy could be reversed. But apart from that little tangent, we've now finished our introduction to entropy, where we define the term entropy S as the number of possible arrangements of the particles and their energy in a given system. Tasks, as always, pause, work through these, starting from the bottom, one column at a time, to consolidate all we've looked at with our introduction to entropy today. From here, we'll keep exploring entropy. We'll start looking, at entropy, as a numerical number, comparing entropy values, and really starting to link this with implications for our chemical reactions. So I look forward to continuing that with you next time. Enjoy your day.